All right, let's start. Hello, everyone. This is Dr. Yuzo. This is EC 341 Power System class. Today is our 23rd lecture. Can you guys hear me?
Yep.
All right, thank you. All right, we can move on. This is the Gantt chart I'm sharing on the screen, and we are right here at this very cell, the lecture right before the Thanksgiving break. Okay. And it's supposed to be the very last lecture for our module 6, the transmission line model. And let's see if we can make it. And if not, we can continue by next lecture, which will be next Monday. Okay. By the way, the quiz 3, hopefully you guys have noticed that the time is actually moved to next Monday. Okay, available from the end of next Monday's lecture and due by 24 hours from then. And by checking the Canvas, you can see all of these details. Okay, quiz 3. All right, and we can move on now. First of all, we didn't do the second part of the example 1 for short line model. However, I'm presenting the answer, okay, for the example 1, second part, which is for the load B, okay, because first part pretty much is for load A, second is for load B here. Okay, so these are the answer. The sending end voltage, the voltage regulation, and efficiency. Okay. And here we are seeing a negative voltage regulation. And we had a discussion about it last lecture. So, by the way, can you guys see my screen here under the dog count? All right, thank you. Thank you. All right, so this is the answer. Okay, as your exercise, you can go ahead to try the load B, and to verify these answers. Okay, short line. This is about short line. Okay, and today we're going to continue to talk about medium line. Okay, medium line. Medium line. And the first thing we need to emphasize is, again, is the boundary, the distance boundary. Okay, so it's between 80 kilometers and 250 kilometers. Okay, this is the distance. Okay, which model we should use is up to the distance. The distance. So medium line model. So first, the model looks like what? So the model circuit. A model circuit. Once again, this is a per phase. Okay, that's a per phase. Per phase circuit looks like this. Well, so far the circuit is exactly same as what we learned from the short line model, right? So obviously the point is, what's the difference between the medium and the short? The difference is here. Medium line model has two capacitance. They're called shunt capacitance. Shunt capacitance. And in the transmission line, we call them the shunt we give them as shunt admittance. Okay, admittance. And the tricky thing is when we label the shunt admittance, okay, this is half, this is another half. It's a little bit tricky here. So the given admittance is actually Y itself. However, in the circuit, each capacitance here is representing half admittance. Okay. And we will see the example for the details. And here, this guy remains same as what we learned previously. Right? The total impedance equals to the resistance plus the j omega inductance, and then times the distance, right? So R and L here are the resistance and inductance per unit length, right? L here is the length. This is the circuit. This is the circuit model. Okay. So the difference is, once again, you have shunt admittance. Shunt admittance. As in the short line model, we are trying to express Vs and Is in terms of VR and IR. Okay. We are trying to derive these two. This is actually a 235 knowledge. This is nothing but a 235 knowledge. Okay, so let's see. So first of all, Vs equals to what? Vs equals to what? It equals to Z times IR plus VR, right? Due to this KVL inside of this loop, right? Anyone? Once again, we are trying to derive Vs and Is. They're labeled here in terms of receiving end voltage and current, VR and IR. Right? Based on this loop, KVL, I end up with Vs first of all equals Z times IR plus VR. Any questions? Because this is not right yet, right? Kevin is kind of figured this out. Where is the mistake? What's the mistake? How to correct this? Can anyone tell?
I wouldn't really say that Z times IR is necessarily true.
That is not necessarily true. It's absolutely untrue. Right, everybody?
Yeah.
So
the current flows through the Z is absolutely not IR. Okay, you can't do that. And this is the basic 235 knowledge. A current flows through here. You can name it with different name as I sub L, which is not absolutely not equal to IR, right? And of course, IL is not IR, not VR either. So we are trying to substitute IL in terms of VR and IR. Any idea how to substitute IL in terms of VR and IR? Any idea?
Well, we know that the current is going to be from VR through the capacitor, across VR through to the capacitor. We know V divided by, well, in this case, it's not the admittance, it'd be multiplied by. So VR multiplied by 1/2 plus IR is going to be IL.
Very good. Very clear. Yeah, very clear. IL, first of all, equals to IR plus the half Y times VR. Did it make sense? This is nothing. This parenthesis is nothing but IL. What's the principle behind we're based on? What's the principle? Anyone? What's the principle here? Typing. Current law. Current. that is a current law, but it's KCL. It's a KCL. KCL means, and this node, if you write KCL, what do you end up with? Current going into this node equals to current leaving it. This current plus this current equals to this current. The current down here is current through this admittance equals to the voltage times the admittance. Exactly, KCL, right? KCL. And then from here, this is the Ohm's law. This is nothing but Ohm's law, right? So voltage across admittance, if you're using a current, equals to the product between the voltage and the admittance. So now we are seeing VS is completely in terms of IR or VR, right? If you organize it, what do you got? 1 plus C times be very careful here is capital and capital Y, the line in admittance and line impedance, the product between them. And this is the equation. This is one equation you definitely gonna use. Vs equals to this. Once again, the idea is trying to find Vs, the sending end voltage, based on the receiving end voltage and current. Similarly, IS equals to what? IS equals what? Okay, give you guys couple of minutes. Try to do this to avoid any rusty from the 235. Okay? This is something very basic. You can't say you don't know this. IS equals what? Also in terms of VR and IR. 235 knowledge.
IS equal to VS times half Y plus IR plus half Y times VR.
I think it's close. Let me see. Okay, maybe I didn't follow exactly right. Yeah, that's the answer. But first of all, you are using a KCL at this node, right? So therefore, the IS equals to this current down here flows through half Y here plus the IL, right? And the current flows through here is equal to VS times the half Y, then plus the IL, right? And then if you further, you need to, obviously you substitute VS by the previous equation, right? So half Y times is a big bracket. Right? Plus IL. IL now we know is actually equals to the second KCL here. So it's IL equals to IR plus half Y times VR. Right? It's a, well, right? So two KCLs, but basically two KCLs. And the further we derive this and try to organize it into a format, you are seeing the coefficient of VS, VR, and the coefficient of IR, right? So IS, and then you basically organize this here, and then you end up with what? You end up with this, right? Y times 1 plus ZY divided by 4 times VR. This is the coefficient times VR plus another coefficient times IR. This is the equation for IS. How to find IS? Here is the equation. Here's the equation, right? So take a look to see any questions. Right. So this is a pretty much review 235 knowledge. No, yep, not check your answer. And Kevin said he missed one IL. Yep. And how about others? Any questions? Any? All right. If that's fine, we can move on. So we have VS and IS once again in terms of VR and IR. And if we define this, define A equals to 1 plus Z times Y divided by 2. B equals to Z. C equals to Y times 1 plus ZY divided by 4. D equals to 1 plus ZY divided by 2. If we are designing this, what do we end up with? We are ending up with this. They're ending up with a matrix operation, okay? So vector VSIS equals to a matrix with entries A, B, C, D times VRIR vector. because sometimes we probably going to use MATLAB to do the calculation. So by defining A through D here, in terms of course, ZY, we can simplify the simultaneous equations a lot. And of course here, this is find VS and IS from VR and IR. And we are doing this, right? And of course, we are able to go the other way around, right? How to find the VR and IR? Right? Right. Any questions? Yep, I think Noah got it. This is wrong, right? Yeah, this operation is absolutely wrong, right? What's the mistake? Noah said it's pre-multiply. What does it mean by pre-multiply?
The inverse matrix needs to go in front of VS.
Yep, here we go. That's right. Okay, this is the right way. This is the right way. Okay. These two need to be swapped. Okay. This must be. Here is a little bit a matrix math here. Say we have matrix A, which is equals to matrix B times matrix C. And if we want to find the matrix C, what do we do? Left times B inverse. Okay. You see, you place your B inverse the left to BC. You need to do so as well on the other hand of the equal. Therefore, you got B inverse matrix times A equals to C. Okay, this is how you find a C. This is how you find a C from A equals to BC, right? This is the matrix operation. And because the two matrix A times B not equals to B times A. Okay, this is the matrix one of the rule of the matrix operations. So that's why. In other words, VR IR equals to right. By the way, how to find the inverse matrix of a matrix? It's very complicated. Okay, it's very, very complicated. However, this is just a 2 by 2, right? A 2 by 2 is fairly easy, right? Anyone remember how to find the inverse matrix for a 2 by 2 matrix? Anyone knows? But actually is like this. Okay, so it's a matrix 2 by 2 divided by a determinant. Okay, determinant in the denominator is easy, just A, B, C, D, the original matrix determinant, and then in the numerator, what do here is swap the main diagonal 2 entry, keep the position of the off diagonal 2 entries, however, give them what? Negative sign, right? So this is the inverse matrix of 2 by 2. And how to do this in determinant? Determinant equals what? 2 by 2.
AD
AD
minus BC.
Correct. Okay, AD minus BC. And of course, we know A through D in terms of D. And if you really do the algebra, actually the result is fairly easy. Yeah, the result is fairly easy. 1. It is equals to constant number 1. Perfect. Couldn't be better, isn't it? It couldn't be better. So the result is this. Here is the find BR and IR from VS and IS. Okay, so here, one way, this is the other. And make sure you're copying the correct formula for everything, okay? And also A through D. Okay? They must be correct. Otherwise, actually, I'm checking if I am copying the right ones as well, okay? Seems I'm okay. Hopefully you are too. Yeah. Find VS, IS based on VRIR, the other way around. Okay. So, and also you need ABCD. ABCD are all in terms of Z and Y. That's Z and Y. Okay. But by example, you will understand better how to find Z and Y in detail. All right. This is find voltage and the current. And next, let's talk about the voltage regulation. But first of all, the voltage regulation, the definition, there's no way to change. Okay, it doesn't matter short line or medium line. The definition of one concept never change. Can never change. It remains as the receiving and the voltage at no load magnitude minus the receiving end voltage at full load magnitude divided by the receiving end full load voltage magnitude. Percentage, right? In percentage. And this is exactly same as what we learned from short line. The difference is obviously the full load and no load voltage, right? So first of all, the full load means what? Anyone remember? Full load receiving end voltage, how we got them? Based on the short line model. Knowledge. Anyone still remember? Yeah, you should be flipping your notebook. Anyone? You find full load receiving end voltage equals what? Given. Good. Haven't got it. This is given. Okay, this is the easiest one. Okay, that's the easy answer. The full load receiving end voltage is given. Okay, and the problem is that we're talking about 230 kilovolt. It's actually receiving end voltage. Receiving end voltage. Receiving end voltage. And does it matter to be line voltage or phase voltage? Does it matter? You got to be careful on this. Okay. In this equation, it doesn't. As long as you keep both no load and the full load voltage uniform. In other words, your no load voltage here is line voltage, then your full load voltage need to be a line voltage too. And then when you do the division here, it doesn't matter, the result remains same as using the phase voltage. And then next, no load voltage at receiving end equals to what? If you recall the short line model, it equals to Vs, right? How about here then? Because we have different circuit, okay? So don't forget. It was equal to Vs in short line model because of the short line model circuit. And here, what is it equal to? Is remaining up to the line model circuit. So let's take a look at these. Okay. Anyone can draw a conclusion what our VR no load equal to. I give you guys 1 or 2 minutes. Try to derive this yourself. The circuit as well as the equations. Okay, maybe equations is more visualized, easier to catch. But here's a Vs and no load voltage. Well, Kevin is basically correct. Kevin is basically correct. Okay, I think he is exactly correct. Yep. Here, it's actually not that difficult. So first of all, Vs equals to this 1 plus Zy over 2 times Vr, right? When no load, what's the immediate consequence? No load means what? Remember that? I emphasize that concept in the short line model. What's the immediate consequence? No load. No current. Good, very good. No current, but specifically, no what current, which current? We have so many.
There should be no IR. If
there should be no good. Therefore, go back here. No low voltage means what? IR equals 0. IR equals to 0. And then you go back to here. Then the Vs just equals to 1 plus Zy divided by R times Vr. And from here, you derive Vr basically. Right? That means Vr equals to 1 plus Zy divided by 2 times Vs. Or just equals to A times Vs. Because we have defined A as this, right? Just equals to A times Vs. I mean, this is Vs. This is VR backwards. So it equals to VR equals to Vs divided by A. VR equals to Vs divided by A. Here we go. VR no load, of course, equals to Vs divided by A. Any questions? Yep. Now Kevin's answer was right. Was correct. This is how you calculate the voltage regulation for medium line model. And last one, of course, the efficiency. This remains same. This remains same. Okay, no reason to be different. No reason to be different. Receiving end active power divided by the sending end active power. But let's recall how we got them respectively. Anyone remember how we got them? In say example 1, we get them.
And do we convert the apparent power from the polar form to rectangular?
That's right. So basically, yep, basically Nora is right. They're from the apparent power, right? From apparent power you can tell. Right? And the apparent power obviously respectively equals to conjugate 3 Vs Is conjugate. Or given. The power might be given. Or given. The basic idea you need to have. Right? You need to have basic idea. Right? Efficiency. The power given may be given power magnitude with power factor, right? So there you need to conduct some calculation like you did back in module 2. Okay, so this is a medium line model. Any questions before we have a example here? All right, if these are fine, then we can go ahead to have an example. Medium line, and here, first of all, you have transmission line 130 kilometers with our base parameter as lowercase r equals to 0.360 per kilometers. L 0.8 millihenry per kilometers. And capacitance equals to 0.0112 microfarad per kilometer. Receiving and voltage 3 to 5 kilovolts and 270 kilo omega VA at 0.8 power factor lagging. Find BS, IS, VR, and efficiency. So here telling you the RLC about the transmission line, also voltage of the receiving end, power of the receiving end. Telling you the voltage and power. So let's do this problem together. Let's do the problem together. First of all, what we need to find? Anyone has any idea? First of all, what we need? Any thoughts? First step.
Find the transmission line.
Find the transmission line. What do you mean by that? There are a lot of things about transmission line. We can't find a transmission line. We need to find something of transmission line. Right? So what is that something?
A resistance.
Resistance is already given.
Impedance.
Impedance better. So specifically, what is it? We need to find a Z, right? And also we need to find a Y. Does it make sense? Z is out of course, in our mind is because of the R and L, right? Y is because what? C, right? So Z equals to R plus J omega L times the distance, right? And Y equals to what? Anyone knows Y equals to what?
That should be 1 over Z.
One,
Since we're
1 over ZC, right? Does it make sense? It's 1 over ZC. Right? So let me give you a 3-4 minutes to find these two parameters, Z and Y, respectively. Find a Z and Y yourself. Let's see what are you gonna have. Let's see what are you gonna have. Of course, here the transmission line assumed to be 60 hertz. Go ahead, use 3-4 minutes to try to find a Z and Y value. You will find, well, not that easy. All right. Anyone got any value? What is Z value here? Kevin, yeah, Kevin definitely has some answer here. Yep, Kevin got the correct Z value. And I think I don't have to repeat the calculation, but I need to remember, okay, be careful. Milli here. This inductance is milli. This inductance is milli. So if you realize that and be careful of that, you should end up with this Z value. Of course, don't forget to times the distance, 130. Don't forget to times that. 4.68 plus 39 J ohm. And Y equals to what? This is actually, generally speaking, student has trouble with. First of all, what are you expecting to see this Y? Y is induced by C, the capacitor itself. So what you're seeing, or what you're expecting to see, the Y value is a pure imaginary number. Does this make sense? Because there's no R, only C. Right? And therefore, in details, actually, how to do this. Anyone? Well, that's fine. If you can make some mistakes in the class, then that's your pressure. Okay. Always said this. Anyone else get any Y value? It's supposed to be pure imaginary number. Right? If that makes sense to you. Anyone else? Trust me, in the past classes, the calculation of this medium line model problem is a huge problem. The calculation, okay, that's why I'm on you to try out in the class time. What's the answer, John? Anyway. Hello? Anyone hear me?
Yeah, I can hear you.
Oh, thank you. Any other answers? Yeah, I figured. Yeah, John's sound is very blurred. Oh, good, very good. John got the correct result, actually. Sorry, Kevin. But anyways, let's see how John get there. Okay, how John get there. It's a 548.9 micro. Micro. What's the unit? S. Kevin is right in terms of the unit. Very good. Okay, so micro Siemens. Okay, how we get there is here's the equation, right? So first of all, the ZC is equal to nothing but XC, right? Or say JXC. And of course, don't forget to times the distance. And the folder is equal to what? So 1 over, what we want to do is here is negative J over 2 pi times F times 0.0112 times 10 to the negative 6, right? And then times 130. Does this equation make sense? The denominator here, this is the JXC. And then this result is going to be 548.9 J. Micro Siemens. Well, micro Siemens. Any questions on Z and Y? I believe most of you guys know the equation, but yep, Kevin missed the distance, and then if others not getting the correct result, you need to figure out where is the mistake. Okay, because if you don't figure out now, you're gonna make the same mistake in the exam. Okay, that's for sure. And people behave in patterns. Okay, that's for sure. All right, if this is fine, then what's the next? Obviously, we want to do the ABCD. Okay, we want to find ABCD. I'll give you guys another 5 minutes to find ABCD. Go ahead. It should be easier, actually. Should be easier than ZY. Go ahead. B is something very easy because B is just equals Z, right? You don't need to worry about B. B is easy. ACD. Go ahead. ACD. All right, let's see the solution here. Okay, it's nothing but applying the equation, or say the formula here. A, B, C, D are defined here, and follow them exactly to do the algebra work. Well, A and D are equal. Okay, be careful. A and D are equal. You don't need to repeat the calculation. A and D are equal. So A and D are equals to this. Okay, 0.989 plus 0.00128J. Okay, E obviously the same. C equals to, well, C is very troublesome, unfortunately. And it's just equals to this. 93.525 times 10 to the negative 7 plus 0.00056J. Any questions? Any thought? Well, it's purely algebra, but however, due to the digits, it's obviously troublesome. Here we go. 4 equations, 4 letters, yeah, for A through D. Any questions? Any thought? What are the units for these? What are the units for these? They have no well, the thing is, these they have how to say this? This ohm times Siemens. What is the result? B is ohm, yes. However, B is representing the value of Z. It's not really anything. For A, ohm times Siemens equals what? Times Z times Y. What's the unit? Can you see it? Nothing. No unit. Divided by 2, no unit. Plus 1, no unit. B is, how about C? Following the same idea, this is supposed to be Siemens, right? Yeah. D is what? No unit again. So A through D, they're not having uniform unit at all. So they're just representing 4 values. 4 values. Okay. And going back to the equation here, that's how we find out the unit. This is how we find out the unit. Okay, it's fine. Then we can move on to the next. After having A through D, okay. Now the next is actually is just to find VS and IS. VS is what one of the questions being asked, and IS we still need it. Okay, IS we still need it. For what? Anyone knows what we need IS for? Anyone understand? Because it is not directly asked. It's not asked. And then what we need IS for? Any expectation? Find IR. Well, no. We can find IR based on the given VR and very good. There is. So here is right. IS is for finding the efficiency. Of course, he is skipping the middle step. We need what? Efficiency requires P, right? P requires S, right? S requires what? Voltage and current. Okay, this is logic. This is logic. Okay. Anyways, VS equals to, obviously, is A times VR plus B times IR. Right? IS equals to C times VR plus D times IR. This is the result of our previous matrix, right? Remember? This is the result of translating the matrix back to simultaneous equation. We know A, B, C, D already. We know A, B, C already. VR equals what? Anyone knows? VR equals what? This is the problem. VR equals what? From here. Exactly. Very good. 325 divided by square root of 3 kilovolts. And also, these are what? This is power factor 0.8 lagging. This is what? Magnitude of SR, right? Magnitude of SR. Not SR, not SR yet. It's magnitude of SR. This is the same thing we need to do in example 1 for short line model. We know the apparent power magnitude and the power factor. We can find the what? We can find IR, actually. We can find IR. So here, VR equals to 3 to 5 square root 3 kilovolts. And SR equals to 270 mega VA. And the power factor equals to 0.8 lagging. It can give us what? The impedance angle, right? Impedance angle. Positive 36.87 degree. And then therefore, the SR in phasor equals to what? Equals to 270 as magnitude with angle of positive 36.87 mega, of course, mega. Right. And this is equals to 3 times VR times IR conjugate. Okay. And from here, you are going to find IR. You are going to be able to find IR. Right? So it's SR divided by 3 divided by VR, and then do a conjugate, ending up with this 479.64 angle of negative 36.87 ampere. We get IR. And then going back to VS and IS, we know VR, we know IR, so we got everything. Again, IR here, VR here. from here, we eventually got Vs and Is. Vs and Is. And Vs equals to 199.1, angle of 3.99 degree, kilovolts. Current is 421, negative 25.56 degree ampere. Yeah, the algebra is intensive. Yes, it's intensive, but it is what it is. Yeah, it is what okay. This VS IS. Now I'll give you guys 5 minutes to continue, try to finalize the voltage regulation and efficiency. Voltage regulation and efficiency. Go ahead. Excuse me. Let's see what you can end up with. All right. Efficiency and voltage regulation. All right, 2 has got the, I believe is correct, voltage regulation. Let's see how we get there. Okay. So VR equals to obviously 2 magnitude, okay? Yeah, 3 magnitudes actually, including the denominator. Numerator is VS divided by A. VS is this value we already got degree. Kilo. Okay, be careful. It's kilo. Okay. Divide by A. A is what? 0.989 plus 0.00128 J. And then find the magnitude of it. Minus 325 is also kilo, divided by square 3, divided by 3 0.25 kilo divided by square root 3. Right? And then what I have is 7.28%. What I got is 7.28%. This is the voltage regulation. And as to the efficiency, what do we need? SR, find a PR. Right? SS, find PS. Right? SR is here. SR we already got here. Right? We already got here. We convert this to PR plus J times QR. Rectangle form, we are able to easily find PR. PR is just equals to we can do right. How to find a PS? A PS need SS. Don't forget, we already got VS and IS, right? We can find SS. And the real part of it is just a PS. Okay. PS turned out to be megawatts. Efficiency is equals to PR, PS, and then equals to anyone got the efficiency actually? Yep, Kevin is right. It's actually 98.74%. Yep, 9.7. That's correct too. Yep. And these are VR and efficiency. So take a look to see any questions. All right, I think that's all for today, and thank you for attending today's lecture. And see you guys all after the Thanksgiving break. Enjoy the break, okay? And don't forget quiz 3. Okay, don't forget we're gonna have quiz 3. Okay, and next Monday, the end of next Monday, pretty much. Thank you, guys. All right, bye.